Hi, this is chapter 14, and it discusses the package of the CMOS chip, um, and it gives some general information, and we will go over some of the basics in this lecture. We're not going to get very deep in this lecture. The lecture number is 5, so we'll talk about some packaging information, and we'll talk about the package types, um, the heat, power distribution, the power supply drop, and the bypass capacitor. Okay, all right. So the package function. So why we package this? You will see this black plastic cover for the chip, and inside it you will see the CMOS die right here. Why do we have this package? Well, there are for the most three main functions, and the very first one is we provide electrical connection of between the chip and the board. So basically, this chip will be sitting on the board, right? Um, and so to provide this connection, okay, that's the job of the package. Uh, Obviously, you would want to do this with very little delay or distortion or drop in the signal level. The second important purpose is that you provide mechanical connection of the chip to the board. Basically, somehow you provide this frame so that this chip can be placed on the board. Also, we need to be very uh, cognizant of the heat dissipation that happens in the die, so we need to remove that. Um, we need to protect the chip from any mechanical damage, and we need to have some compatibility with the thermal expansion. Obviously, this anytime you place a material on top of another material and heat comes in or generated from within, if they don't have the same thermal expansion, then you will end up with funny shapes for the two materials. So and this bending could happen. So you have to be very careful with the thermal expansion of the materials that are glued or attached to each other. Uh, Finally, important that this packaging will be cost effective. Okay, all right. So these are the three functions or the three main characteristics of the package. Historically, through-hole packages were used in the past for these chips. You can see that these chips have pins, and they kind of go through holes inside the circuit board. Surface mount packages then came along, where you basically the packages are soldered to the surface of the printed board, and this alleviates the pin inductance and hole size. So there are other types of packages, and try to minimize inductance on the pins, maximize number of pins, it's reduce the cost. So therefore, the various types of packages. Um, if we look at the basic through hole type, and we kind of do a cross section, here is the die right in the middle here. Okay, and then you have in this die, if I just magnify the die, you will see these pads on the die. Whoops, these pads on the die. So those pads on the die. Okay, and so this is the die here, and these are the pads, and basically those pads, they kind of provide a connection between the bond wires and the die. So these are the bind wires right here. These are the bind wires. So the bind wires comes in here and connects to this lead frame. Okay, so these are the bind wires comes in here and connect to the lead frame. And the lead frame, which is right here, distribute signals in the package. And also we have some kind of heat spreader. Okay, so that helps with the cooling, so you can kind of help in dissipating the heat generated in the die. Okay, now um, the another packaging type is the flip chip, and this is basically you have metal pads on top of the die, and then we place solder balls, and then we kind of flip the chip upside down, and then we carefully align those solder balls on the board. Then heat melts those balls to where the chip is placed. This is referred to as C4, which is controlled collapse chip connection. Again, it's all about we're trying to reduce the contribution of parasitics, and mainly parasitic inductance in those bond wires. Now, um, we let me just yeah, that's the image that I want to show. You can see that here is the die or the chip, and there are the wires leaving. The bond wire connects me to the lead frame. Okay, so this is the bond wire, this is the lead frame. These bond wires have parasitic inductance, resistance, and capacitance. We don't want these resistance and capacitance and the inductance, but they exist because we are using physical material. Okay, so they tend to create issues for me, and this chapter try to address those issues. Okay, um, first of all, one of the before we dig in, heat seems to be an important factor in the designing of package. If you consider a light bulb with 60 watt, and of course that's an old light bulb, by the way, which has an area surface of 120 square centimeter. Then you compare it with the titanium to die, which dissipates 130 watts over 4 square centimeter. Obviously, the power density, which is the power over area for the titanium, is much larger and huge. So we need to consider cooling, and it's an important factor that we cool down the die before it damages the silicon and the device. Okay, so obviously we have to do some kind of heat spreading to a larger surface area. You can think of the heat sinks. They improve that by having those. It's almost like have those extra area for those fins where they dissipate the heat. We can use fans. Okay, that increases the airflow, and we can use liquid cooling, which tends to be a bit expensive side. Okay, so these are three sometimes you can combine, for example, heat sinks and fans. That provides for you uh, better cooling. Okay, so heat is a problem. If not addressed, the device will be damaged. Now, one of the things that we need to study here is that the relationship between the temperature and power dissipated. And it turned out if you have a this is your chip here, and this is the ambient. Whoops, sorry, that went too far. And this is the ambient here, okay? And suppose you have this is the temperature in the chip, or we like to call it junction here. And this is the temperature of ambient, T ambient. Between the two, we have some kind of packaging material or no material. Obviously, we would like to approximate this with some kind of thermal resistance. So here is we approximate it with some thermal resistance, which is between the junction, which is in the silicon, and the ambient, which is the outside. It turned out that if you subtract the temperature from the junction minus temperature of the ambient, that is equal the power generated in the die times the thermal resistance between the junction and ambient. So this relationship between power, okay, and the difference in temperature, which is the delta T here, it tells us to what temperature we can work this device. Now, obviously, because here there is this package here, uh, this package here consists of, or the ambient here, there is this package in between here. Okay, so this really theta between, so this is the package here. Okay, so this theta here has to add two thetas, which is the theta between the junction to package and package to ambient. So junction to package and package to ambient. Okay, so these are the two thermal resistance, and they turned out they are added in series, much like a electronic resistor. Okay, so here's an example where we can say that if we have a chip right here, okay, and this chip, right, there is a package here. So this is the package for the chip, and this is my chip here. Okay, and there is a heat sink with a thermal resistance to the package of 4 degrees per watt. Okay, 4 degrees per watt. So basically, between the package and the outside, let me use another color here. Between this is the thermal resistance between the package. So this is between the junction, between the package and ambient. The thermal resistance, which is the outside world, the thermal resistance equals 4. Okay, and the resistance from chip to package is 1 Celsius per watt. So this is here the thermal resistance between the package to I'm sorry, junction to package equals 1. So this is junction to package equal 1. Okay, and now the system box, the outside temperature may reach up to 55. So the outside world reaches to up to 55 degrees Celsius, and the chip temperature, we have a restriction that this chip temperature should not exceed 100 degrees. Okay, so what's the maximum chip power? What is the maximum chip power? Okay, so we apply this formula. All right, so I know this chip, which is 100 minus 55, which is the ambient, equals to the thermal resistance of adding these two series becomes 5 degree per watt. So I plug it here times power, and it turned out 9 watts is what gets me to 100 degrees here. If I consume or dissipate 9 watts of power, my chip temperature goes up to 100. And that is, if I consume 9 watts, if I consume 10 watts, then I will exceed 100 degrees, and my device will be subject to damages and shorts and short circuits and etc. Now the question is, how do I measure temperature inside the die? How do I measure temperature inside the die? How do I measure this? Well, we have inside the die a temperature sensor in which I have basically two BGT devices, PNP. Okay, and there is a current injected I and M times I in one of them, and there will be a developed different VPEs because of that. Okay, and what I need to do is measure those VPEs. If I run the equations for the current that goes through the collector from your electronic course, we can express that as so, and we can write the VPE in terms of the collector. Okay, like so in this equation, and for the delta VPE between these two BJT devices can be expressed as such. Okay, and you can do simplification and reach to this term right here, which is what I want. Okay, and obviously this K is this Boltzmann constant. This is the temperature, which is absolute temperature. This M, I know it. The Q for the charge on electron, I know that. And now, if I measure this via analog to digital converter, I have all the things that I want except this that can find out. So this is, I can measure it, the delta VPE. This is a constant. This is a constant. I know this value because I control it, and now from that I can get T. In fact, you can pre-cook those numbers in such a way that you can have a table inside your chip where you have here the delta VPE and the corresponding temperature. So you sense the value of this. This is the temperature for it. So let's say point, for example, 0.5. It is, for instance, for example, I'm just giving an example here. It is 35, the temperature. Point 0.06, it is 37, etc., etc. Okay, so you can pre-calculate those numbers. The PNP device is can be implemented as such, where you have the P plus diffusion in well. The base can be connected, but we need an N plus material here to connect the base, and we can have the collector, which is the P plus material in the substrate. So obviously the emitter, the base, and the collector. Okay, PNP device. Okay. Now, next we would like to talk about power distribution network, and clearly this power distribution, it carries the current from the pads to the transistor. And if you look at, this is basically our chip here, and we would like to know if we have here, let's see, so this is our chip here. So we have down here, there's a transistor, and we are sending VDD here. So this is inside this. So what's the value of this VDD here through this power supply network here? And obviously this VDD is coming through this package from the power supply source. What happens here? So obviously this power distribution network, we need to carry current from pads to transistor. We want to maintain stable voltage with low noise. And why stable? What happens? Well, if you draw lots of current, then the voltage fluctuates. We need to provide average and peak power demands. So obviously peak power when you are executing lots of, for example, floating points. Um, we need to provide current return paths, and that relates to the ground. You obviously don't want to have different values of grounds. We need to avoid electromigration and self-heating. Electromigration, it's more of those wires that carry DC current. Like for example, if we are sending a power supply wire, so you will see electrons will always move in one direction. They tend to erode the wires in certain way, and at the end this wire will fuse if you are not careful in designing this wire. So this problem called electromigration. as opposed to self-heating. And self-heating, it happens for the wires where current go back and forth. And a good example for that, a wire which carries the clock. So the clock, we charge discharge this wire. And that if you continue, if you're not careful, then obviously when we charge and discharge such a wire, it will have a heat. So that self-heating problem would wear out the wire if you're not careful of designing the wire. Okay. And all on top of that, we would like to have as minimum area as possible for wires, and easy to be laid out on the chip. So these are kind of the goals and constraints for power distribution. If you look at as I drew it a little bit earlier, if you look at, this is my chip here, and inside the chip you have the on-chip capacitor here, and then you have these solder bonds, and which has some inductance and resistance. And then you go out to the package. This is my package here. Okay, so this is my chip here. All right. Again, those package pins and frame, they have resistance and inductance and parasitic capacitance. I have to deal with those. And then when you go out to the board level, to the board, okay, so that's the board. Again, I'm gonna face those parasitic inductance and resistance, all right, and capacitances, and that will kind of, introduce issues to my power level. So I have to consider those in my design. It is important that we understand that there are two sources of a drop of VDD. So basically, this again. I'm going to draw this. This is my chip, and this is my transistor inside the chip. Okay, and it turned out. Oops, sorry. Let's see. It turned out. When I take this VDD all the way to here. Okay, so this VDD value is different than this VDD here, and there is some kind of IR drop, and then the outside the chip and the package all the way to outside the package, there is this I LDI over DT, okay, DI over DT. L is the inductance times di over dt. So both these factors cause current, and let's see what they are. So this factor here, which is due to the resistance of the distribution network inside the chip. This is due to the distribution of power network inside the chip. So we are inside the chip. We are inside the chip. So whatever current goes through this network, we multiply it by its resistance, that will cause a drop. So if we have, say, for example, IR drop here equals 0.1 volt, then this value here will be 0.1 volt less than this value. And then the other DIDLT, L times DIDT, this happens in the distribution network, which is outside the chip. This is outside the chip. Okay, so this is outside the chip in the package and the board level. And typically this happens whenever I have change in the current. Okay, that's why you have DIDT. Both factors will change the value of the VDD that eventually reaches the transistor. So both factors will cause for me a drop. So the sources of this drop, okay, are these two. 1, 2. Inside the chip, outside the chip. Caused by resistance, caused by inductance. Okay. Now, so in terms of the IR drop, which happens inside the chip, right? What I need to know, I have to add the resistance of the power distribution network of all the wires that carries the VDD, and I need to know the current that goes through these wires that supply VDD. If I multiply the two, then I get the IR drop. Here's an example. A chip draws 24 watt from a 1.2 volt supply. The power supply impedance, which is right here, okay, is 5 milliohm. What is the IR drop? Well, first of all, I have to find the current, okay, because I need to remember, I need the I and need the R. The current, I can divide the power over the voltage, and then I get the current, which is 20 amp. Then the IR drop is the multiplication of current with the impedance of this network, and it ends up being 100 millivolt volt. Now, um, let's talk about the other type, which is LDI dt. Basically, whenever the current changes outside the package, right, this sudden change over di over dt multiplied by the inductance, it causes a drop in the power supply. So why outside the package? Why not inside the chip? Why outside the chip? Well, the inductance inside the chip typically ignored. It's not as much. This becomes pronounced outside the chip. That's why we care about it outside the chip. Okay, so here's an example. It says that you have a 1.2 chip switches, 1.2 volt chip switches from idle mode or transition, consuming 5 watts to full power, 53 watts. Okay, there is a transition because this is going to impact this guy now. The transition takes 10 cycles at 1 gigahertz. 10 cycle, that's the DT, right? Okay, so the power supply inductance is zero point 0.1 nanohenry. What is the LDI dt? LDI dt. Okay, I know that the L is right here, provided for me. What's the DI? Well, the DI, I know we are going from 53 watts to 5 watt. In a volt of 1.2 volt, that provides for me the delta in the current, which is 40 amp. So that is my DI. Okay, that is my DI. Okay, now how about the DT? Well, that happens through 10 cycles. Every one of those, because the frequency is 1 gigahertz, is 1 nanosecond. That is happens. This change happens in 10 nanosecond. In 10 nanosecond. Okay, so all now LDI dt, just plug in the numbers, the inductance, the current, the delta I, the delta T, and you get 0.4 volt. Okay, now because this is huge, what we do to reduce these fluctuations, what we do is we provide a bypass capacitor. And the bypass capacitor, basically, it's a reservoir of charges that sit here, so that it provides this demand of current when it happens all of a sudden. So it will alleviate this demand, and I wouldn't have these shocks of DIs on the system outside, because I know DI over DT times inductance will translate into drop in voltage. So if I can minimize this DI, well, how do I minimize it? By provide a reservoir of charges, which is the capacitor. We call those the bypass capacitors. So the bypass capacitors, they need to supply sudden spike of current. In this example, we need a current of 40 amp. This will be needed in 1 nanosecond. And we don't want a fluctuation or a droppage more than 200 millivolt. So the equation of the capacitor is the current through capacitor is delta V over delta T. So delta V, this is the delta V across the capacitance. Delta T is the 1 nanosecond. So here is the delta V, which is we don't want to be more than 200 millivolt, and the delta T here 1 nanosecond. Okay, and the current that we need to supply is 40 amp. We need to find C. It turned out to be that C is 200 nanofarad. That's large, by the way. Okay, so unfortunately, the bypass capacitors, they are not ideal. You would want to have just a capacitor here. For example, this is 1 microfarad, but it turned out that it has a parasitic resistance and inductance. Because notice that the ideal capacitance, its impedance is equal to 1 over, whoops, 1 over j omega c. So if I have here frequency and this is the impedance z, so you will see that this is the impedance. Unfortunately, so this is just for a pure capacitor, but because I have an inductance and resistance, the impedance of the practical capacitor, physical capacitor, will look like this. Okay, why after it dipped it goes up? Because what happened, you have this resistance and inductance. This becomes the impedance of this capacitor. It will include the parasitic resistance, the parasitic inductance. Okay, and it will continue reducing the impedance until I get to the resonance, right, frequency, where the capacitance is canceled by the inductance and you just have the resistance. Okay, and in this case this is the resonance frequency. It is equal to 1 over 2 pi square root of LC. So for example, if you have a 1 microfarad capacitor, 0.25 nanohenry, and this is the resistance, the capacitor has low impedance near resonance frequency of 100 megahertz. Okay, so that's the resonance frequency, and so this kind of changes the impedance per frequency because of this parasitic and resistance. But with all the issues that comes with these bypass capacitors, we need them, as we said, to supply current and to reduce the change in DI, so that we don't have a drop because of DI dt times inductance. And this is pretty much what I want to say. And we'll stop at this. Again, this model of the chip resistance, right? And this is the package inductance and resistance, and this is the board inductance and resistance, and this is really the big picture here, where you have to include all these parasitics in your system model. Thank you very much.